So that takes us to our lecture material for today. I should warn you that nearly all of the material in today's lecture will review stuff that you should have learned back in freshman chemistry. Nevertheless, it is pertinent groundwork for understanding the rest of organic chemistry, so we will cover it. Are you ready then? Good. Let's get started. After today's lecture, you guys should be able to do the following: distinguish between ionic and covalent bonds, explain electronegativity, identify nonpolar and polar covalent bonds, and draw Lewis structures, Kekulé structures, and condensed structures. First, I'd like to start by reviewing the difference between ionic and covalent bonds. You see, when two atoms bond so that they share each other's electrons, we say that they have formed a covalent bond. When two atoms bond so that one completely steals the electrons from the other, more or less, we call it an ionic bond. Here are some pictures that show how electrons spread across three different molecules. Redder parts of those molecules have more electron density, that is, there's greater partial negative charge there. And bluer parts have less electron density, which means that there's a greater partial positive charge there. Our first example, F2, shown here, which is also known as fluorine gas, is formed when two individual fluorine atoms bond together. When they do so, they share their electrons. Thus, we can say that they form a covalent bond with even sharing. In our second example, HF, or hydrofluoric acid, the H and the F atoms also share each other's electrons. Unlike F2, however, H and F do not share those electrons evenly. So this is an example of a covalent bond in which there are uneven sharing of electrons. In our third example, LiF, or lithium fluoride, the lithium atom has more or less completely transferred its single valence electron to the fluorine atom. Thus, these two atoms are not sharing electrons. Instead, the fluorine has more or less completely stolen the electron from the lithium. This type of bond is called an ionic bond because there's a complete transfer of electrons, leaving two individual ions, a lithium positively charged cation and a fluoride negatively charged anion. As mentioned, when covalent bonds form, sometimes the atoms in those bonds share their electrons evenly, and sometimes they don't. So what determines the degree of sharing? Electronegativity. And what is electronegativity? Electronegativity, simply defined, is an element's thirst for electrons. The more an element wants to steal electrons to feel like a noble gas, i.e., obtain a full octet, the more electronegative that atom is. Electronegativity increases as you move up and to the right on the periodic table. Noble gases, the elements found in column 8 of the periodic table, are excluded because they have very little thirst of electrons because they already have a full octet. Thus, the most electronegative element on the periodic table is fluorine, and the least electronegative atom is francium. This brings us to an impromptu lecture question. Which atom in each of the following pairs is the most electronegative? Now, I'm not going to answer this question for you, but will instead let you ponder and answer it for yourself. This is, of course, an excellent exercise to determine if you can identify trends in electronegativity. As I've already foreshadowed, when two bonded atoms have an electronegativity difference, the more electronegative atom will hog electrons like this. In this example, chlorine is much more electronegative than hydrogen. Thus, the chlorine pulls electrons to itself much more strongly than the hydrogen does, kind of like a tug-of-war between a monster truck and a Volkswagen Beetle. This uneven sharing of electrons results in a partial positive charge on the hydrogen and a partial negative charge on the chlorine. This charge difference is called a dipole. The greater the difference in electronegativity between two atoms, the more unevenly they share electrons and the more polar their bond will be. We can often say then that bonds with dipoles, that is, uneven sharing of electron, have dipole moments. We can draw a dipole moment in two different ways. One way is by drawing a partial positive charge next to the atom that has a partial positive charge and a partial negative charge next to the atom that is more electronegative. Another way is to draw this. This little arrow pointing toward the more electronegative atom, the one that is hogging the electrons to itself more, indicates that the electron density is more heavily accumulated on that atom. Covalent bonds with dipoles are called polar covalent bonds, and covalent bonds that do not have dipoles are called nonpolar covalent bonds. So this takes us back to our original slide here. As you can see, when two atoms have an even sharing of electrons, they have a nonpolar covalent bond. This happens when they have little to no difference in electronegativity, as occurs in F2. When two atoms have a more significant difference in electronegativity between them, they unevenly share electrons. This is called a polar covalent bond. And lastly, when two bonding atoms have a really significant electronegativity difference, one atom will completely transfer its electrons more or less to the other and form an ionic bond. We might consider ionic bonds then to be kind of like extremely polar covalent bonds. This occurs most often when an atom from the right side of the periodic table bonds with an atom from the left side of the periodic table. Because they have such an extreme difference in electronegativities, they will form an extreme dipole, in essence a complete transfer of electrons from one atom to the other, giving an ionic bond. This brings us to another impromptu lecture question. Arrange each of the following sets of bonds in order of increasing polarity. And question 2, which of the following bonds has a dipole? For those that have dipoles, on which atoms do the partial positive and partial negative charges lie? Once again, I'm not going to answer these questions for you, but will let you instead ponder and answer them for yourselves. We now move to a different subject, that of Lewis structures. Back in general chemistry, we learned how to draw Lewis structures. Now, I expect you to know how to do this, but I will not give a thorough review here. Instead, I will just summarize the steps, give you some example problems to practice with, if you wish, and provide some helpful links to online tutorials on the subject. If needed, please review section 1.4 of our class text. So here are the steps for drawing Lewis structures. 1. Add up all the valence electrons for every atom in the molecule. If there are any anions in the molecule, add 1 electron to the total number for each negative charge. For cations, subtract 1 electron from the total number for each positive charge. Don't worry about which electrons came from which atoms. Only worry about the total number. 2. Write the symbol for all the atoms in the molecule showing which atoms are attached to which. Then connect them with a single bond or a dash, which represents 2 electrons. Chemical formulas are often written in the order in which the atoms are connected. In many polyatomic ions, the first atom in the formula is the central atom in the Lewis structure. Usually, but not always, the central atom is the less electronegative atom. 3. Complete the octets around all the atoms bonded to the central atom except for hydrogen, which only wants 2 electrons around it. 4. Place leftover electrons on the central atom even if doing so results in more than an octet of electrons around it. And 5. If there are not enough electrons to give the central atom an octet, try multiple bonds, such as double or triple bonds. You got that? All right. Here are some more lecture questions on the subject. Question 1. Construct a Lewis structure for O2 in which each atom achieves an octet of electrons. 2. Explain why it's necessary to form a double bond in the Lewis structure of O2. And 3. Draw Lewis structures for each of the following molecules. And here's another question. The Lewis structure for the carbonate ion is what? Now, once again, I'm not going to answer these questions, but will instead let you answer them for yourselves. We'll now finish this lecture by briefly introducing you to 2 different subjects, Kekulé structures and condensed structures. In Kekulé structures, bonding electrons are drawn as lines, and lone pairs are usually left out unless needed for some special reason. Here are some examples. We often draw simplified structures by omitting some or all of the covalent bonds and listing the atoms with subscripts like this. These types of structures are called condensed structures. The condensed structures shown here correspond to the Kekulé structures that I showed in the previous slide. And now I finish by showing you some more lecture questions on this subject. Question number 2 from our problem set. The Kekulé structure of pentane is shown here. Draw its condensed structure formula. Question 3. Write a Lewis structure for the following molecule, CH2CO. And question 4. Draw Kekulé structures of the 5 different isomers of C6H14. Well, that brings us to the end of this lecture. Please stay tuned for a part 2 lecture on electronic structure and bonding, which will be posted shortly. Until then, have an enjoyable day.